started here. And I'm going to pass the row sheet around. Well, I'll just pass it first, and then people who come late will come back to me and roll it back. Do that. Yep, the class is definitely getting smaller. There's more oxygen available to everybody.
Maybe that's why the grades are better.
Sorry?
That's why the grades are better now?
So yeah, you're just going to hear a lot of sighs.
I have a question.
Yep, go ahead.
What's the name of that theory that states that matter can only hold so much information? I think it was information theory, but I'm not certain.
I cannot remember.
I had to explain it to my psychology teacher because he was talking about like the possibility that the mind could have truly unlimited memory. No, physics says no. I said even if it's got like
So you're talking about the number of states that can be represented by a certain thing at a quantum level, right?
I'm guessing like just sort of the general idea that states that matter can only contain so much information. Because even if it's something really outrageous and huge, it's still limited. Infinity is infinitely larger than any infinity.
But there are different levels of infinity.
True, but he's talking about like truly unlimited.
No, there's not. It's a concept.
But the whole point is the human mind has a finite amount of memory.
That's what I was trying to get across to my teacher.
All right, and within a finite amount of memory, only a fraction is retrievable. The rest is lost. It's like, yeah, I know it's somewhere in here, but I cannot get to it. Yep. All right, so we are now talking about section 5 or by-value parameters, which is a very useful idea because the main difference between a local variable and a by-value parameter seems very simple, right? They share a lot of common things. They're both allocated on the fly when a subroutine is invoked, okay? They both use up one extra column per invocation, per variable. One is initialized by the invoke statement. The other one is uninitialized when you get into the subroutine. So the differences seem to be very minor, but that one difference of having a by-value parameter initialized by the invoke statement makes it very useful. Because now the invoke statement has a way to pass information into the subroutine that it is invoking. It's acting like an inbox, okay? It's acting like an inbox where the subroutine can take that information, do something about it, and basically say, okay, I'm done, and not having to worry about all of that stuff later on. So that's why by-value parameters are actually very useful. We'll go ahead and write a subroutine today, to begin with, that will just kind of demonstrate how useful a by-value parameter is. And we'll use recursion again. In other words, we'll have another version of the recursion. We'll have another version of the recursive factorial program to illustrate why by-value parameters are so useful. So let me create a folder for today first, and then we'll continue. All right, so let's go ahead and write the algorithm first. Define sub, factorial, and this time we have by-val n. Okay, so n is the input parameter. Now the other thing that we have to kind of keep in mind is a by-val parameter is only useful as an inbox, but it is useless, completely useless as an outbox. So at this point, we don't really have any mechanism as an outbox other than a global variable. So we still have to use global variable at this point, as an outbox. But at some point, we'll be able to get rid of get rid of global variables altogether. Global variables are really, really bad because they make programs a lot more difficult to maintain. Okay, so that's why we want to eliminate the use of global variables altogether at some point. All right. Can anyone kind of imagine why global variables they make things a lot more difficult in the long run? Yep.
If you are using global variables, you have that extra information being held when you may not need it anymore. Plus, if you're trying to use the same variable to
because it can be corrupted by just about any subroutine. So if you have a global variable and you have 2,000 subroutines, any one of the 2,000 subroutines can potentially access that one global variable and mess it up. Okay. And the other thing is, when you look at the subroutine, just the beginning part of a subroutine, you have no idea of whether that subroutine can mess around with a particular global variable or not. So that means the side effect of changing a global variable can be very stealthy. Okay, it's really hard to spot. And someone can introduce one single line of code in one of the subroutines and mess up the entire program. Okay, so that's the kind of thing that we want to avoid. Okay, you cannot avoid having bugs and mistakes altogether in programming. I mean, that's just human nature. Okay, we just make mistakes, but you want to make the mistakes or the bugs easy to locate. That is the bottom line. Okay, the bottom line is not how many lines of mistakes you can write per day. It's how quickly can you locate those problems and fix it. Yep.
Is that the same vulnerability that hackers use to access people's laptops or?
No, not quite. That's not really quite the same thing. They used to use what we call stack overflow exploits and also buffer overflow exploits. Those were effectively gone by the time we have the execution inhibit bit in processors. So the new exploits are something that's different. And for the most part, the exploits these days are focused much more on websites than individual computers, because you can hack a website just by injecting certain types of queries in the URL, and you can dump out the entire database, including the client name, client ID, passwords, and all this stuff. It's much better than hacking individual computers. Yep.
I remember hearing about an article how there were some students that were expelled or something because they were messing around with the URL because it wasn't protected. They just typed in like test answers and they got expelled for quote unquote hacking just because they were messing with the URL.
Yeah,
They weren't even doing anything that much other than changing a few things.
Yeah, well, in that case, I think I think the problem is the script itself is not secure. It also has to do with the intention of the students. I guess that is a part of the factor. In other words, in a much more traditional setting. Okay, so let's say I have my key, the answers to my exams laying around somewhere. Okay, so if a student go there and go, oh, okay, here's a key to a test, and I'll go make some photocopies of that. So is that act wrong, or is it who's wrong in this case? The professor who kind of did not secure the key, the piece of paper, or the student who saw that and go like, hey, I can use this opportunity to make some copies out of it. So it really boils down to the same thing. I think it really is the same thing. It's just that one is electronic and the other one is physical. So I think the students should still be responsible for the action, but whether it's enough to be expelled depends on I guess the college policy. It also depends on how the student use that information. If it's really just for fun, it's like, oh yeah, we can get this information out of the system and not do anything about it. That's one thing. But getting it out of the system and actually make use of that information in a wrong way is another thing. So it's hard. It's a hard call unless we know the more details about it. Okay. All right. So getting back to factorial. So this time we can make the factorial program a little bit easier to understand, and actually easier to write too. So we'll still say the same thing. If n is greater than 1, then we'll do the recursion. But this time the recursion is easier because we can just say invoke factorial again. N minus 1 specifies n. I know it's kind of confusing having n on both sides, so we'll talk about this when we are ready for that. And then we'll say the result is the result, whatever it is at this point, times n, else the result is 1, and if, and define sub, and then here we just say invoke factorial. Let's see, let's just try 2 factorial. Good enough. So here's my entire program. We'll just fix the indentation. I just like this part of using a spreadsheet because I can select individual cells and then move, do the indentation all at the same time. Okay, so here we have our new algorithm. Well, it's the same algorithm factorial, but this time making use of bi-val parameters. Let's make sure that we save this file to today's folder. Factorial using bi-val parameters. There we go. Can anyone spot any global variables in this case? We only have two names actually used. Is there a global variable? R. That's right, R is our global variable because it does not have, it's not local, it's not bi-val, it has to be global. Okay? So that's the convention that we use in this class, which is consistent with most scripting languages like PHP and Perl. In C, you have to declare everything, but in most scripting languages, you don't. Okay, so let's go ahead and trace this algorithm. We have commands for the one condition we have on line 3. We have our usual line number, and R is our global variable. As most global variable, you pretty much have to assume that it is unknown unless I tell you that, oh, guess what, it is pre-initialized to a certain number. But otherwise, most global variables should be uninitialized. Here we go. And we start execution on the first line, the only line that is outside of the definition of a subroutine. In this case, it is line 10. Line 10 simply says invoke factorial, 2 goes to n. Okay, so we have to do the usual thing of allocating one column for the return line number, and then remember where we are supposed to go back to when the subroutine is all done. So return line number is going to indicate post because line 10 is the last line. There are no additional statements to execute after this. But this time we also have to allocate another column because we have a bi-val parameter. Okay, a bi-val parameter, like a local variable, requires a column allocated on a per invocation basis. So here we have n as a parameter. It is allocated, but unlike a local variable, a parameter gets its initial value from the invoke statement. So the invoke statement on line 10 says we want n to start with a value of 2. Okay, so we'll give it an initial value of 2. And this, doesn't seem like a very big difference between a local variable and a bi-val parameter, but it is. Okay, it makes certain things just possible using this approach. Once we have set up the columns, we can continue execution inside the subroutine starting on line 3. Line 3 is a fairly simple statement. N is greater than 1 is true because n is 2 at this point. Then we go to line 4. Line 4 is invoking factorial again, so we have to once again set up a return line number as well as for the parameter n. The return line number is fairly easy. The invoke statement is on line 4, and we do have line 5 that is doing something that's useful, so the return line number is simply line 5. So that one is not too much of a problem. N is a little bit different, because the way we specify this n is to use n minus 1 as an expression. So it seems like we have a chicken and egg problem, because how can we use n, which is to be determined, to determine itself? Well, that's not really the case, because the n of n minus 1 on the left-hand side is using a different n. This n minus 1 is using column E. This n on the right-hand side is specifying column G. So we don't really have a problem, because the left-hand side is using column E. Column E has a value of 2 at this point. 2 minus 1 is 1, and that's why column G now has a value of 1. Is that okay? Are there any questions at this point about why the n of column G has a value of 1?
How do we know it's referencing column E?
Because that's the only one that you know. So you have to utilize what you already know to determine the new columns.
Okay.
Yep.
So if a subroutine invokes itself,
inside the subroutine, then the variable becomes local to that invocation. Does that make sense?
Yes.
Okay.
Yes.
Okay.
The localness, is both in terms of scope as well as lifespan. So it's only local to that invocation. Exactly. Yep. Yep.
So if you have, say, another n on column I, would that be referencing the n on column G?
When you set it up.
Okay.
Only when you set it up. Yep.
So left-hand side refers to what we already know, and the
Right.
right-hand side.
And that's why you see the right arrow, because the arrow indicates, which side do you evaluate first to determine which other side. Okay. So now that we know this part, we can now continue execution at the invoked subroutine. But since we're invoking factorial again, we have to start on line 3 again. And this time n is greater than 1 is false. Now if n is greater than 1 is false, we have to go to the else part, which is only on line 7. Line 7 does only one thing, it just turns r to 1. So r is now 1. After line 7, we get out of the conditional statement. There are no other statements to execute. We get to the end of the subroutine on line 9. Line 9, once again, has two things to do. One is to find out where we are supposed to go to continue execution. The rightmost active return line number tells us we have to go back to line 5. Okay, and then the second thing it has to do is to deallocate the 2 columns that we allocated for this particular invocation. So we'll get rid of these 2 columns. And now we'll continue execution on line 5. Line 5 says I want to evaluate r times n on the right-hand side. Which n are we talking about? Which column?
E.
Column E, because column G is already deallocated. Okay, so our context is now back to column D and column E. Of these 2 columns, column E is the by value parameter n. So we are actually multiplying 2 and 1, and then the product is 2. We store the product back into R. R gets updated to 2. And after line 5, we are getting out of the conditional statement to the end of the subroutine on line 9. And line 9 once again has 2 things to do. One is to look up where we are going to continue execution, which is post. And then the second thing is to deallocate the 2 columns for this particular invocation, and we're done. So are there any questions about this trace?
It really didn't do anything. It really didn't do anything.
But try 3. Yep.
I don't know, it sounds maybe a dumb question, but so yesterday not yesterday, the last class we were doing, it was invoke x times 4 or whatever, and today it's just invoke the factorial. Does the end of the factorial part not matter as much if we're just invoking? Is that just the type of thing we're using? It doesn't change the actual trace, does it? By saying factorial or times 2 or times 4.
That's just a name.
Okay, that's
Yeah.
okay. That's
Yeah, factorial is really just a name.
I saw that and I was
say-
like, is this something different? Because it looks exactly the same. I just want to make sure.
Yeah, I can say define sub blah blah blah.
Okay.
As long as I'm invoking blah blah blah, it will still do the same
What
thing.
does the sub part mean? Sub means the.
Sub means subroutine.
Subroutine.
So we're defining a subroutine. Yep.
Sorry.
So when the variable is local, is there any reason for a use of a forget rule without changing it to a specific value?
That's an interesting question. The question is trying to tie in the concept of a local variable or by value parameter to the pre and post condition thing. Okay. If you want to prove that this algorithm in fact calculates the factorial of n, then you have to go through the same thing with a pre and post condition thing. So in this case, n cannot be less than 0 because the factorial of a negative number does not make any sense. So n has to be at least 0 because with 0 things, there's only one permutation, which is also nothing, right? So 0 factorial is actually 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. So it is kind of interesting if you want to prove the correctness of this algorithm. It involves a particular technique called proof by induction, which is a little bit out of the scope of this class. But yes, you can actually prove the correctness of this particular algorithm using the pre and post condition, in addition to proof by induction. Yep.
By proof by induction, you just mean that we have to, based on the things that we know about what n has to be, then we can infer what it will be.
There are two components to proof by induction. The first one is what we call a base case, which is something that is just, okay, it's by definition. In this case, by definition, 0 factorial is 1. Okay, so that we know for sure. And then you have what we call a step. A step in proof by induction is saying, if we know that this theorem is true for case n, can you prove that it will also be true for case n plus 1? So if you can establish the connection from case n to case n plus 1, and you have a base case, and you say that I know this has to be true when n equals to 0 in this case, then you have just proven the algorithm to be correct for any n that is greater than or equal to 0.
Sounds like a lot like inductive reasoning.
It is. That's why it's called proof by induction. Yep. Instead of deduction, it's induction because we are moving forward and not moving backwards. And that concept is in CISP 440 in discrete structure. They will talk about proof by induction, proof by contradiction, and so on and so forth a lot. All right. So do we have any questions about the concept of by-value parameters? It's a really handy way to get information into a subroutine so the subroutine has that piece of information to compute. So in this case, I'm using n to tell factorial which numbers factorial am I trying to compute. Oh, it's n, okay? But it's not going to be useful for passing information out of a subroutine. So I'll illustrate that in just a little bit. Yep, go ahead.
So with local variables, you're trying to assign a value to the variable inside the subroutine, but with a by value, you're trying to put information into the subroutine.
A local variable stays completely inside a subroutine. So the outside or the invoke statement has no visibility whatsoever to a local variable. It cannot control its initial value. It doesn't know its final value. With a by value parameter, it has one control, which is the initial value of the parameter when the subroutine executes. But it has no knowledge of its final value, which is why it's not useful as an outbox, but it's only useful as an inbox. Okay? So what we'll do next is to show the limitations of a by value parameter so that we set the stage up for by reference parameters. Are there any questions at this point about local variables or by value parameters? Well, I guess the next one will be a good example to illustrate both. So here we have another example. Okay, this one is a fairly simple subroutine that's called swap, okay, or exchange, depending on how you want to spell it. Okay. Swap is going to say by val x, by val y, local t. Okay, so we have both concepts that we have talked about so far, and the next three statements are fairly, I guess, well known. If you want to exchange the values of x and y, you need a third one to remember one of the two, and then the first one can then get the second value of the second one, and then the second one, now that it has its value copied, can get to the original value of the first one, which was stored in t, and that's it. Okay, and define sub. And outside of here we have, okay, let's avoid the use of global variables. So I'm going to switch to the kind of standard of C. You have a main subroutine, and inside the main subroutine we have two local variables. Let's say the first one is, I can use different names. One is called A, one is called B. We'll give it some particular value so we can actually track the values, how it's being changed. B is 7. Invoke swap. I use A to specify parameter X. I use B to specify parameter Y. And define sub. And define sub. That's the main subroutine. And outside of everything, I'm just invoking main. This is the C standard, okay? Because in C, you cannot have any code outside of the definition of a subroutine, but you do have a special subroutine called main, where it is the entry point of everything. So this is to emulate that particular aspect of C and C++ program. Yep.
Can you read that one more time?
That's exactly why we're recording the lecture, right? In C and C++, you cannot define any action, any statement outside of the definition of a subroutine. So that means you cannot say, oh, we'll start executing with the first line that is outside of the definition of a subroutine, because everything has to go into a subroutine. So the only way you can control the entry point of the entire program is to designate what we call the main function or the main subroutine. That is the subroutine that is quote unquote invoked by the operating system itself. When you run a program, it automatically invokes main, and that becomes the entry point of your entire program. Yep.
So you don't have to type invoke main. That's just
In C, you do not. That is
that's
implied.
the way it works. Yeah.
Yep. That's just the way it works. It is implied.
And automatically goes to the subroutine main.
Correct. It is part of the standard specification of C itself. So all C compilers will behave the same way. All right. So I'm just fixing up the indentations here, and then we'll figure out what this program is going to do and why it is not very useful. I mean, some of you can look at this and kind of understand why it is not useful. But to fix it is also very simple once we know what is a pass by reference parameter. So I'll just call this swap using by val parameters, which is not the way to do it, but we'll go ahead and take a look. We don't need comments anymore because we don't have any conditions in this case. We have line number and we have no global variables. Okay, we have finally gotten rid of global variables altogether, which is good. So, well, if you want to say something about the precondition, you can still say something about the precondition, which is nothing. Because we don't have anything to talk about as the precondition. And then we start execution on line 16, which is the only line that is outside of the definition of a subroutine. In C and C++, you don't even have this statement because it's implied. It needs a return line number, which is going back to post. And then we have to allocate 2 additional columns in this case because main has 2 local variables. As local variables, they start with an unknown value. Each one starts with a unknown value. Okay. Once we set up the columns, we can continue execution inside the subroutine, starting on line 12. Line 12, fairly simple. We want A to start with a value of 5, and then line 13 says we want B to start with a value of 7, and then we go to line 14 for the invocation of swap. Once again, it is an invocation. We need to allocate 1 column for the return line number. The invoke is on line 14. Line 15 is right next to it, so the return line number is line 15. And then we have to allocate 1 column for each local variable and by value parameters. This time we have 2 by value parameters and 1 local variable, because we have x, y as by value parameters, and we have t as a local variable. T is the easy one. It's just unknown because it's a local variable. X is specified by the expression on the left-hand side. So in this case, what do you think x should start with? X should start with the same value as A, which is 5. Okay, very good. And Y has a value of 7 to begin with. Now, right here, I should stop just a little bit to basically say we have 2 columns with a value of 5 and 2 columns with a value of 7. And they are independent. In other words, if you look at this picture at this point, okay, let me just kind of fix the width first. if you look at this picture at this point, column C has a value of 5, column F also has a value of 5 because it is a copy, a clone of column A. But at this point, those two columns are independent. Whatever I do to column F is only happening to F. It does not go back to affect column C at all. Okay? So that's a very, very important point, because not understanding this will kind of cause problems later on with passing by reference, which is doing exactly the opposite. Okay, so at this point we can continue execution inside the subroutine swap on line 5. The swap procedure, only consists of 3 lines. T gets the value of x. Okay, since x has a value of 5, T now has a value of 5. On line 6, we copy the value of y to x. Y has a value of 7, so x is now updated to a value of 7. And then on line 7, we copy the value of t to y. T has a value of 5. Y now is updated to a value of 5. So if you just look at the effect of this portion here, the swap logic is completely correct, okay? Because x and y, had their values exchanged exactly as we wanted, right? But the subroutine is entirely useless, because the next thing we do is going to go, oh, okay, so why did we do all that stuff? Because on line 8, what do we do when we are at the end of a subroutine? There are 2 things to do. Well, the first one is not to deallocate. The first one is to look up the return line number, because once you deallocate, it's not there anymore. So you have to look it up first. So you look up the return line number. It says we have to continue execution on line 15. Okay, that's fine. That's not a problem. And then the next thing, as we said, is to deallocate the columns. So once we deallocate the columns, they are lost. So by the time we continue execution on line, oh, I think I messed up here. No, it is right. Okay. So by the time we get back into the main subroutine on line 15, guess what? A still has a value of 5. B still has a value of 7. What we did was just completely inside the subroutine swap. The result is completely gone. So even though the logic is correct, the result did not stick. Quote unquote, did not stick. Okay. So we will just go ahead and finish this entire program. On line 15, we also have to do another return, because it's the end of the main subroutine in this case. So we have to say, oh, look up the return line number. We have to continue execution at post. And at this point, we don't need these 3 columns in either. So we'll go ahead and strike these through. And we are done with this trace. So I'm going to save it first, and then I'll save it again using a different name, because we'll change the algorithm just a little bit to fix it. Are there any questions about this algorithm and its trace, and the reason why I said, well, the logic is right, but the implementation is wrong because it's not useful at all? No questions? Okay. So let me save the file again, and this time I will fix it. So save the program again, and this time we'll say swap by reference, which is the other way of passing information around. Okay. Now the syntactical change of this program is going to be very simple. There will be like 4 changes. Instead of saying by val, we say by ref. Okay, that really is just to signify that x is no longer a by value parameter, but instead is a by reference parameter. And the way we pass, using the symbols is also a little bit different, only in this class, because I want to make it very clear that we understand what is the big difference between passing by reference versus passing by value. Instead of using a right arrow, it is now a double-sided arrow. The double-sided arrow in this case is intentional, because it means whatever you do to x happens to a. So it's a 2-way thing. Okay. Okay. So let's go ahead and trace this algorithm, and then see what happens. I will erase everything and kind of fix all the length of the columns first, just so that we start with a kind of blank slate in this case. There we go. All right. So we have the same thing. We start execution on line 16. That part really has not changed, but I just want to do it all over again. We have return line number going back to post, just like last time. We have two local variables, A and B, both starting with a particular unknown value. So that part really hasn't changed much. You know, once we get into main, it's about the same thing too. On line 12, we initialize A to 5. On line 13, we initialize B to 7. But on line 14, things are now a little bit different. We still need one column for the return line number. We still need one column for parameter x, one column for parameter y, and one column for local variable t. Local variable t still starts with an unknown value, just like last time. But what is different here? Okay, the return line number, even that one has not changed. It's just going back to line 15. But what is changed now is how we represent x and y. X is still specified by the expression a, but it doesn't get the value of a. It becomes the reference to a. Okay, so that's the difference. Okay, so in order to represent it without using pointers and addresses and stuff like that, which you will learn in C and C++, as well as in assembly language programming, in this class, we'll just call it an alias of a column, aka column, also known as column C. So x as a parameter is also known as column C. It refers to column C. You can probably imagine what y is, aka column D. It's an alias of column D. Okay, well, that's okay. Seems like it's really the same thing. We just use a different way to call it. Okay, but when we access these, when we access x and y, you will see that there are differences. Now that we have set up all the columns, we continue execution in the swap subroutine. Let me fix column E. It can be a little bit narrower. There you go. Now we continue execution on line 5. Line 5 is not going to show you any difference because the right-hand side says x. Okay, we want to evaluate x. So we go to x and we say, oh, guess what? X does not have a value. Okay, it's really just a reference to another column. All right, fine, I've looked up that column. Column C has a value of 5. Fine, okay, so x really is going to evaluate to a value of 5. So t gets updated exactly the same way as last time. It has a value of 5. The next line is completely different from last time. Because on line 6, the assignment statement says we want to use the value of y to overwrite the value of x. Okay, it's a regular assignment statement. But the effect of this is slightly different. We look up y first because it's the right-hand side. We have to look it up first. It is also known as column D. Column D has a value of 7 right now. So the entire right-hand side of this assignment statement is 7. Okay, that part is not too bad. With that part we can understand. But when we update x, that is where passing by reference is completely different from passing by value. Because when we try to update x, we say, oh, let's change x here. Oh, but hold on a second. X is really just an alias of column C. So we don't change column F, which is x. We change what it is referring to, which is column C. So it is column C that is being updated to a value of, nope. Yeah, to a value of 7. Okay.
Like your spreadsheet program thing that you can type in, like the E3 equals E2.
Yeah, you can do something like that. Yeah, but in this case, it is important to explain why column C is updated instead of column F. Are we still doing okay so far at this point? Okay. So after this, I can give you one analogy where you can easily remember what a reference really is and why you can do things like that. Okay. So on line 7, you can probably guess what's going to happen here. On line 7, the right-hand side is just t. T is a local variable with a value of 5. That part is easy. We want to update y. But y is an alias. It doesn't have a place to store a value. An alias can only refer to another column. So y is only referring to column D. It is column D that gets the value of 5. Okay. happens on line 8? You know what? Line 8 does exactly the same thing as what it did last time. In other words, first thing, look up the return line number. Okay, we continue execution on line 15, and we deallocate all 4 columns here. So we say deallocate, just like that. But isn't that going to be bad? Because last time we deallocated all the parameters and the result of the entire operation was erased. But this time it's okay, because all we are erasing are, well, the return line number is not an issue, the local variable is not an issue, but parameter x and parameter y they are nothing more than aliases of another column. In other words, column C and column D are still the same way as they were right before the end of the subroutine swap. And that's why, quote unquote, the changes is sticking this time. Okay. So when we go back to line 15, it's the same thing as last time. You know, we look up the return line number, continue execution at post, and then we can also deallocate these 3 columns. Okay. So that's why passing by reference is different, because it is not tracking the value, it is only tracking an alias of another column. Are we doing okay so far? So let me give you an analogy. I'll try my best to use an analogy that that kind of resembles all the concepts that we are talking about. If a subroutine is like an office, like a cubicle, okay, a local variable is representing a resource that is completely inside the cubicle. It's not an inbox, it's not an outbox. It's a little pile of post-its, inside the office itself. Okay, so no one from the outside can see it. No one from the outside can write it. No one from the outside can read it. Are we doing okay so far? It's completely inside the cubicle. A pass-by value parameter is not exactly like an inbox. It is more like a copier that has a label of inbox. Okay, so kind of imagine a copier. Let's say this is the cubicle. Okay, and there's a copier that's labeled the inbox. Where the paper comes out is coming into me. So what you are really doing is you're putting whatever you want me to process on the copier. Press the copy button. You keep the original. I get the copy to work with. When I'm done with working with the copy, I toss it into the recycle bin. But I'm not tossing your original into the recycle bin. I'm tossing the copy into the recycle bin. Are we still doing okay so far? Local variable is a resource completely inside the cubicle. Passing by value is like a copier labeled as a inbox. Then what is a pass by reference parameter? A pass by reference parameter is, in a way, it still looks kind of like an inbox with a copier, but you're not making a copy of the original thing. You're making a copy of where I can find the original thing. Imagine the books in the library, okay? So if each of these things is like a book in the library, passing by value means you are giving me a book. You're giving me a copy of a book from the library, and I'm just modifying and changing whatever the copy is. It doesn't affect the original one on the shelf in the library. Passing by reference is like you writing down the call number of the same book, and you're making a copy of the call number itself. Okay? So now I have a call number instead of the book itself, and I can go to the library and find out exactly which book you're talking about, and I can mess around with that book. At the end of the whole process, I still have to toss something into the recycle bin. But what am I really tossing into the recycle bin? A copy of the call number, not the book itself. That is the difference between calling by value versus calling by reference. I mean, passing by value versus passing by reference. Yep.
Okay, bear with me as I organize this in my head properly. So, you said at the top of the hour, or at the beginning of class, that subroutines ruin the global variable.
You do not want to access a global variable directly from inside the subroutine.
Okay, this is where a pass reference subroutine comes in handy versus a pass by value.
Correct, because you want to modify something, the subroutine needs to modify something that does not belong to it.
So when a global variable is corrupt, it's because the programmer used a pass by a value versus a reference.
No, a global variable is a problem when it is directly accessed inside the subroutine. It's not passed as a parameter of any kind. In other words, like right here, if on line 5 I directly access variable, well, I don't have any global here, but if I directly access a global variable within the swap subroutine, that would be bad practice. But if I use a parameter to pass something in, it is not a bad practice. That's the only way to do it. Yep.
So if you wanted to keep the values of the original, say in this example, if I wanted to keep the fact that A is 5 and B is 7, but I wanted to swap them, I would need to create essentially a variable C and D, and then other column W and Z, and then have 2 bivals to bring it in, and then 2 by references to put it back into.
You cannot swap and keep them at the same time. The subroutine can either swap, exchange the values of the 2 parameters, or not touch them, right? So you cannot keep them, and you cannot keep the values the way it was and exchange them at the same time. Because when we say exchange, it implies that it is done in place.
Okay.
Yep.
Can we, kind of like what he's saying, can we keep C and D the same but return something else that was swapped? Can we return something? We haven't done that.
We haven't really talked about the return statement yet, so at this point we don't return anything.
Yeah, that's what I wanted to do.
Okay.
But I'm getting there.
We're getting there. In this case, return cannot help because there are 2 results. Return can only deal with one single
We can
result,
never
but since
return
we have
more
2,
Oh, sorry. We can never return more than one?
not in this pseudocode and not in C that we usually use. There are ways to return multiple things in C, but it's not common. But in this case, are we doing okay so far with the concept of passing by reference? Okay. If that is okay, let's go back and change our factorial program to also make use of passing by reference. Okay, that's actually a pretty easy change. Okay. Make sure we save this one more time, and then we'll go ahead and create factorial again. And this will be the second last revision of the factorial program, because when we have the concept of a return value, that will be the final one. That will be the cleanest implementation of factorial. So define sub factorial. We have an input of n because n is passing into the subroutine to tell me the factorial. We are trying to find the factorial of which number, and that's n. And then we have by reference r, which is the result. This is the outbox, so-called outbox, because we are using it to know where we're supposed to modify and store the result. The rest of it is pretty much the same thing as last time. If n is greater than 1, then invoke factorial. But this time, in addition to passing n minus 1 to n, we also have to specify what r is. So the way we specify r is r. Whatever is the alias passed to me, I'm passing on to you. Okay? So the next invocation of factorial will also know where to store the result. And then after this, we also update r to r times n, else r gets a value of 1, and if, and define sub. And this time, since last time somebody said, but it doesn't do anything, so we'll go ahead and make n a little bit bigger this time. So we'll put the other one inside main, because we want to use this new standard, right? Put everything into main. And here we have a local variable, let's call it x, to store the result. So this time when we invoke factorial, we can say we want to compute the factorial of 3 and store the result into r. into X. Define sub, invoke main, just like that. And then we can fix all the indentations. There we go. So now we have the second last modification of factorial. Now this one, even though if you just look at factorial, it seems even more cumbersome than last time, but it does have one huge advantage over the previous one. What do you think it is? What do you think is the main advantage of this approach versus the previous one?
Members.
It has no global variables. And that's a big one. It's really, really important. Let's go ahead and trace it and find out how it can get everything done but without global variables. Comments, line number, and this time we have absolutely no global variables, so there's really nothing to say about the precondition. On line 15, which is the only line outside of the definition of a subroutine, we're invoking main. We have return line number telling us to go back to post. And then we have one single local variable called x, which starts with an unknown value. Then we continue execution inside the main subroutine, and it only has really one line that is useful, which is line 13. Line 13 invokes factorial, so now we have to store the return line number again. This time it's returning back to line 14. And in terms of allocating the extra columns, we have parameter n and parameter r. N is passed by value, so it simply has a value of 3 because the invoke statement says that n should start with a value of 3. So that's the easy one. R, on the other hand, is specified by x, which means R should become an alias of x. Which column does x live in?
D.
Column D, so R becomes an alias of that. So R is now an alias, aka of column A, also known as column D. Are we doing okay so far with this trace? Then we continue execution inside factorial, starting on line 4. N is greater than 1 is true because n is 3 at this point. So we go to line 5. Line 5, now this is going to be a little bit messy because I have to scroll kind of a little bit more. Let me see. Okay, I'm going to split the screen into 2 halves. So this way, the comments and line number would not move, but the other part can move. Okay, that's okay. All right. So now we are on to line 5. Line 5 says I want to use the n that I already know to compute n minus 1. That value will specify the new n or the column that I'm trying to set up now. So let's go ahead and label all the new columns first. The new columns I'm trying to set up still includes a line number. And we can make this one a little bit narrower so we can fit more stuff on the screen. So we have a new line number, and then we have a new n, and then we have a new r. N is the easy one to deal with because we are using the existing n minus 1 to specify the new n. The existing n is 3, 3 minus 1 is 2, so this n passing by value has a value of 2. The return line number is also easy because we come back and we continue execution on line 6, so the return line number is line 6. R is kind of the questionable one because it seems like we have 2 ways of going forward from here. We can either say that this R is an alias of column G, or we can keep the same thing and say this is just another alias of column D. Okay, do you guys see what those 2 options are? It is the second one that we always choose. In other words, when you pass a parameter that is already passed by reference to you, and you need to pass it by reference to somebody else, you are just passing the reference along. You're not going to pass a reference to a reference. Okay, so you have to remember this. We do not daisy chain references. But both because of efficiency issues, as well as in C, there's no way to do this. Okay, there's just no way to know that this is a reference of a reference. So R in column J is exactly the same thing as R in column G because they are both aliases of column D directly. Are we doing okay so far with this concept? Okay, because it's an important one. Okay. All right, now that we have the columns all set up, we continue execution again from the beginning of the subroutine that we're invoking, which is factorial. On line 4, n is now 2, 2 is greater than 1 is true. We go to line 5, we pretty much do the same thing. So on line 5, I'm going to use, just copy and paste here and just change the one cell that is different. The one cell that is different is n. So n is now going down to 1. And then we continue execution on line 4 again at the beginning of the subroutine that we're invoking. Line 4 is evaluating the same condition, but this time the result is different because n is 1, 1 is greater than 1 is false. So that's why we don't go to line 5 anymore, we go to line 8. This is the end of the recursion. In other words, we are not invoking factorial again from inside factorial. It is also equivalent to the base case when we prove by induction. On line 8, we simply change R to 1. So we look up R and say, oh, R is an alias of column D. So that's why we are not even going to mess around with all the other columns. We just go straight to column D and say, you are getting a value of 1. Are we doing okay so far with this step? Because this is the important part, is the subroutine is not modifying something that belongs to it. It's modifying something that it knows how to access, but it belongs to somebody else. But was it authorized? Yep, the access was authorized because it was main who originally says, you know what, if you want to store the result, store it into X. That was the original authorization to overwrite column D. Okay, so it's not like with global variable where you just kind of grab a global variable and say, I'm going to change that. Okay, this one you still require the invoke statement to say, you know what, I'm going to tell you what you can modify, and this is what you can modify. This is how you find that's something that you can modify. And it's not up to the subroutine to decide randomly and go, I'm going to go change column D. Okay? Now this restriction is a big one. Okay, you can still have problems, have bugs and whatnot, but because of this restriction, it makes it very easy to track down problems because a subroutine without accessing global variable cannot just randomly change something. It has to be something that the invoke statement says, yes, go ahead, you can change this. Okay, so now that we know how this works, after line 8, we get out of the conditional statement, we go to line 10. The rest should be fairly boring because we know that stuff already. On line 10, which is the end of a subroutine, we track down the return line number first. We say we continue execution on line 6. Then we have no use of these 3 columns anymore. Strike them out. And now we continue execution on line 6. But since column K, L, and M are gone, we have to kind of roll back a little bit to find out what is our current existing context, which is now columns H, I, and J. On line 6, we want to compute the product of R and N. R is referring to column D. Column D has a value of 1 at this point. N has a value of 2. 1 times 2 is 2. We store the 2 into R. R, once again, is referring to column D. So column D is the one that is updated to a value of 2. Are we still doing okay so far? Okay. And then we get to line 10 again. We get out of the conditional statement, get to line 10. And line 10 has, once again, 2 things to do. Look up the return line number. We continue execution on line 6. And we also have to indicate that these 3 columns are now deallocated. Just like that. Now we're back onto line 6. But columns H, I, and J are no longer our context because they are deallocated. Our context is now back to columns E, F, and G. On line 6, we once again want to compute the product of R and N. R is referring to column D has a value of 2, N has a value of 3, 2 times 3 is 6. We store 6 back into R, and R, once again, is referring to column D, so column D is now updated to a value of 6, which is 3 factorial. And then we get out of the conditional statement, go to line 10, has 2 things to do. Line 14 is where we want to continue execution, and then we have no use of these 3 columns anymore. Deallocate, and now we continue execution on line 14. Line 14 is not really doing anything useful because it's just the end of the main subroutine. We continue execution at post, and then we deallocate the 2 columns for this invocation, and we are done. So are there any questions about the trace of this particular algorithm? No questions? This is okay? All right. So it seems like we have all the mechanisms that we really need for subroutines. We have a way to pass information into a subroutine. We have a way for a subroutine to modify something as the output of a subroutine. But we still have one more concept to talk about, which is the return value. So why do we need to talk about return value as a way to pass information from inside the subroutine back to the outside or the invoke statement when we already have passing by reference? Well, this is, for the most part, a convenience feature. Okay? So think about it like this. Let me save this first, and I'll give you an example where it'll be kind of clear that, yeah, that's kind of cumbersome. We really need a better way to do something like that. Okay, so we'll have this one called factorial using by, val, and also by ref. Okay, so we have both passing by value and passing by reference in this case. So let's go ahead and create a new one as our new example. Okay. I just want to make a subroutine that adds up 2 numbers and then store it, and return the value, return the sum. Okay, that's all it does. Okay, is to perform the addition operation. So using the stuff that we already know at this point, we kind of know how to do it. We know that in order to add, we have at least 2 numbers to add and then 1 number to store the sum. So we have by val A, by val B, and then by reference the result, which is R. Okay, and we just say R is getting the value of A plus B and define sum. Yeah, no big deal. It's pretty easy to do. And then we can do the same thing with multiplication. So we can say define sub multiplication by val A, by val B, by reference R. R gets A times B in this case, and define sub. In other words, I'm just using subroutines to replicate things that we can easily do with an operator. But the whole point here is to illustrate why passing by reference is really kind of cumbersome to use as a means to get a result out of the subroutine. So now we have defined sub main, and I'm going to use this as an indication of comment. In other words, everything that starts with the pound sign. Actually, in this class I should use // because you're moving on to C and C++ and not Perl. I just use Perl a lot myself, and I use pound to begin all the comments. So // in C and C++ means everything after the // are considered comments. In other words, it's useless to the compiler. The compiler just kind of ignores whatever you say after the // Is that okay so far? So it's just a notation. You can add comments to your own program, and this is what I'm doing here, is to just put some comments here. And because I want to say what I really want to do. So let's say we want to compute 3 plus 4, and then the whole thing times 7. This is what I want. Oh, maybe times 9. Okay, this is what I want to do. Okay, we already know this is just 63, but I want to use the subroutines that I have in order to finish this computation. We have to first deal with the addition, because that's the one that's the operation in parentheses, and then we have to perform the multiplication. I cannot do anything without using an additional variable, right? Because if all I really want to do is to print the value of 3 plus 4 and then times 9, I cannot just say print blah, 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 blah. I need a place to store the results, okay? So that's already one little indication that it's kind of cumbersome, because now I need to use a local variable to store the sum. Well, I need only one r here, and I'll show you why I can reuse the r. So I have a local variable called r, let's call it x, so we don't reuse the same name. Okay, so the first thing we have to do is to invoke the add subroutine to perform the add operation. So in this case, we specify e to go to parameter a, we specify 4 to go to parameter b, and then we specify x to specify parameter r to store the result. And then the next thing we do is to perform the multiplication operation. But to use the multiplication operation, we can reuse r to specify a, we can use 9 to specify b, and then we can use r again, oops, sorry, we can use x to specify r. Take it back, this one should be x as well. That will be fine, because I can reuse x in this case without a problem, because the first one is passed by value. In other words, I'm just saying, okay, what do we have in x right now? Make a copy of that and make it parameter a. The other x is passed by reference, which means r will become an alias of the column that is storing x. So it's not conflicting. We can use it this way. Yep.
In C and C++ on line 14, where you open it with comments, you don't need to close the comments?
No. With // you do not close. With /*, you have to close. So if all I really want to do is to print out the result of the computation, this is what I have to go through, which is not exactly intuitive. I mean, it's doable, but it's not exactly the shortest way to do it either. Okay. But in normal calculation, how come we don't have to do something like this? It has absolutely nothing to do with the fact that we're using infix. Okay. In other words, okay, so this is a good digression at this point, is to talk about the 3 ways of expressing your usual arithmetic operations. So let me make sure we save this one first, because it is important. Okay. It will say clumsy passing by reference, okay? Because it is really clumsier than what it has to be in this case. So I'm going to use mousepad here as a whiteboard to specify the 3 ways of expressing an operator. We have the usual way of what we call infix representation. Infix representation means this is how we represent the operation. 3 plus 4, the whole thing times 9. This is the infix notation. Infix means the operator that specifies what we want to do is in the middle of the 2 things that we are doing something with. So in this case, the addition operation is specified by the plus symbol, but the 2 things that we are adding are on the 2 sides of the plus symbol. And that's why it's called the infix notation, because the operator is inside. It's between the 2 things that we are supposed to operate on. Are we doing okay so far? And this is the way we are used to. But it really is one of the worst representation. So in this class, in many computer science classes, you will start to question, why do we learn things like this? Why do we use base 10 instead of base 2? Why do we have infix notation instead of postfix or prefix notation? Okay, so this is what we call infix notation. There's a prefix notation. A prefix notation means you represent the operator first, and then you specify what is operating on. Okay. It may look a little bit strange to you because because we are specifying the plus first, and then we say, oh, what are we adding again? Oh, 3 and 4. Okay, and then you specify the multiplication because we have to take the sum of the addition operation, and then specify that we want to multiply that to 9. Is that still okay? I mean, it's awkward looking, but for the most part, it still makes sense. Yep.
There's a schema, right? So that's the programming language that
Scheme, yeah, just scheme or Lisp. Yeah. Scheme is kind of like a dialect of Lisp. They're all like this. They're always using the prefix notation. So this is what we call the prefix notation. You specify what you're going to do, and then you specify what it is going to do something with. But we have seen this already in this class, haven't we? Your typical invoke statement is exactly like that. Because you say invoke and then the name of the subroutine, and then you specify the parameters that you're passing into the subroutine. So in a way, subroutine invoking is using the prefix notation. It's just that we have long names instead of using a symbol, but nonetheless, it is the same thing. So prefix is not too bad, but there's another one called postfix. Now postfix is the really, really odd one, because you specify the things first, and then you specify what to do with it. So in this case, you say 3, 4. Oh, what are we going to do with 3, 4? We're going to add it. What are we going to do with the sum of 3, 4? I don't know, but we'll specify another number first, 9, and then we'll do a multiplication. That is the postfix notation. Also, otherwise known as RPN, or reversed Polish notation. Yep.
Is that prone to error? Is that prone more to human error?
No, it's not. Okay, how many people know someone who is an engineer in his or her at least about 40s or 50s right now? Okay, have you ever asked that person for a calculator? No? Okay, because if you had, you would notice that that calculator is most likely an HP calculator that can only understand RPN. And then you say, I want to calculate this expression here, and then you go, but where's the parentheses? There are no parentheses on those calculators because there's no need for parentheses in reversed Polish notation. So an entire generation, or at least 2 generations of engineers, can look at an infix notation, not simple like this, but a really long, complicated one, and in their mind, convert it directly to postfix notation when they use the calculator. Yep.
What's the point of having that?
That's a good point. That's a good question to ask. Why do we bother with these strange notations? The prefix we can kind of understand, right? Because it is really the same thing as invoking subroutines, okay, in a way. Because once we understand return values, it's really the same thing as invoking subroutines. The postfix notation is there because the early HP calculators have limited computation and storage ability. In order to parse open paren 3 plus 4 close paren times 9, you need to have a parser on a calculator to really understand what that means. And that's complicated. Okay, it really is kind of complicated compared to the other one. The postfix notation is extremely easy to implement from the calculator's perspective. And that's why it is used. Because it doesn't need parentheses, it doesn't need any parsing, and it's very easy to implement.
So is it basically because we didn't have the technology before?
That's because we didn't have the technology before with HP calculators, and it's an easy way to get around it.
So if they're teaching engineering students now, do they still teach them that way, or do they teach them the modern way?
Well, HP calculators are no longer the mainstream calculators. I think TI are now the mainstream. So that's why people don't use postfix notation anymore, except when you take a look at PS files, PostScript files, as well as PDF files. If you look into the actual content of a PDF file, they're still using the postfix notation. Okay. Does anyone know what is PostScript? PS, the extension PS.
Isn't that dealing with fonts and stuff?
Well, you're close. Not fonts, but how to draw something on a piece of paper or on the screen. Okay, so I know I'm digressing a little bit here. How do you send a bitmap to print to a printer? So let's say you're trying to print Mickey Mouse. Okay, so yes, Disney can sue me. Okay, so this is what you want to print, solid. Okay. So this thing is solid, and you want to send it to the printer to print. Okay. Okay? What are you going to do to send it to the printer? There are two ways to do it. One way is what we call the dot matrix way, okay, or raster way. The rasterization means you are really looking at this thing as pixels. And you're specifying each individual pixel to the printer. Okay? You're saying off, on, off, kind of on, off, and so on. You send all that information to the printer, and the printer is going to render the dots accordingly, on a piece of paper. But that's going to take a long time when you have a printer that's capable of 1200 dpi by 1200 dpi. 1200 dpi means 1200 or 1200 dots per inch, right? So if 1 square inch has 1200 times 1200 dots, how big is a page? How many pixels do you have on a single page? A lot, okay? So even with USB 2.0, it's gonna take a little bit of time to send all those dots over, okay? So this is okay when we only have like 9-pin dot matrix printers in the good old days, but not so good anymore with high resolution laser printers. Yep.
And you have to send it by vector, basically saying,
right.
Okay, draw a circle from
Yep.
this point.
That's exactly what PostScript is about. PostScript is basically saying, you know what, I'm going to specify there's a solid circle here. This is the center, this is the radius, and this is the color. Another circle is over here. This is the center, this is the radius, and this is the color. And then we have a big circle here. This is the center, this is the radius, and this is the color. That's all that is sent to the printer. And at the printer will do all the rendering and know how to print the image out. So the communication between the computer and the printer is kept to a minimum. It's the printer's own responsibility to render this into a raster way and then specify how to put the dots on the piece of paper. So you have co-processing in that case. The PC doesn't have to do a whole lot, just send over simple instructions. It's up to the printer to decide how to print it out. So PostScript, P-O-S-T-S-C-R-I-P-T, PostScript is using the postfix notation. In other words, when you specify a circle, you specify this is the center, 2 numbers, this is the radius, 1 number, and then this is the color, or you can set the color ahead of time, and then you just say draw circle. So draw circle automatically knows, oh, so I need to use the previous 3 numbers to draw that circle. Okay, and it is used exactly because in earlier printers, computation power as well as RAM is a premium. They don't want to waste all that stuff just to do infix interpretation. So they use postfix because it is very easy to process. And even today, when you look into a PDF file, which is also from the same company, from Adobe, a PDF file internally uses exactly the same same representation. It is still using postfix as a representation. Okay. If you look into compilers, okay, if anyone has a chance to look into the internal workings of a compiler obviously has to understand infix, right? Because this is how we specify expressions. But when it spews out the code, the object code to the processor, all that stuff is actually converted into somewhat like a postfix notation. This is a number, this is a number, this is what you do with those numbers. This is another number, this is what you do with that number. Okay? So postfix, even though we don't use it anymore, the computer internally is still using that in a very significant way. Okay? But getting back to our point, driving this all the way back to where we left off, this is what we want to do. In other words, we want to say the subroutine called add here is going to return a value. In other words, the invocation of add can be treated as a value itself and be immediately utilized in any place that we can expect an integer. That's what we want to do. Are we doing okay so far? So let me just say that one more time and then we'll end today's class. What we want to do is not something that looks like this because it is extremely cumbersome. What we want to do is to say, we can use an invocation of a subroutine in place of anywhere that can expect an integer. Okay, so that's why we have return values. Yep.
Is that saying that you want to use it as a parameter?
Yep, because you can use an integer to specify a parameter. So once we know how to do what I just said, then an entire invocation of a subroutine can specify a single parameter. That becomes extremely handy. So that's what we'll do next time on Tuesday. Have a nice weekend.